In this video, we are going to introduce the fundamental counting principle and talk about the concept of permutations. Our learning objectives are to use the fundamental counting principle to calculate the value of factorial expressions. We will look at how to find the number of permutations of n objects and how to find the number of permutations of n objects taken r at a time, and then find the number of permutations when some objects are alike. In the previous video, we introduced some basic concepts of probability, and we talked about sample spaces as the total number of outcomes in a probability experiment. And we looked at some simple cases like flipping a coin, rolling a die, right, where the total number of outcomes is something like 2 or 6, some pretty easy small number. When a sample space is small, like outcomes for rolling a single die, you can literally list and count them. But as probability experiments get more complicated, we are going to need to learn some techniques that go beyond simply listing and counting. So we're going to take a break from probability for the next 2 sections, and we'll study 3 basic rules for counting the number of outcomes for a sequence of events. The first of these 3 rules is called the fundamental counting principle. Fundamental counting principle. Let's say that a hip furniture boutique has the couch you want in either leather or micro suede, and each comes in your choice of 4 colors. How many different couches do you have to choose from? We will illustrate the situation with what we call a tree diagram, which displays all the possible combinations, right? We can choose from either leather or micro suede, and regardless of whether we choose leather or micro suede, we can choose one of 4 colors: tan, white, red, green. Tan, white, red, green. Each of the colors at the bottom of the diagram actually represents a totally different couch, right? For example, if you follow the left branch at each stage, left, you will get a tan leather couch. The 8 branches at the bottom show that there are 8 possible couches. Notice that this is the same number you'll get if you multiply the number of choices at each stage. Right? The first stage has 2 choices, leather, micro suede. The second stage has 4 choices, tan, white, red, green. 4 times 2 gives me 8. Now, what if each couch can also come with or without an end recliner? Each of the 8 choices in our diagram would have 2 more possibilities beneath it. This would give us a total of 16 couches. This would be 2, right, times 4 times 2, which again is the product of the number of choices at each stage. This illustrates our first counting principle. The fundamental counting principle. In a sequence of n procedures, if the first can occur in k1 ways, the second in k2 ways, and the third in k3 ways, and so on, the total number of ways the sequence of procedures can occur is found by multiplying these numbers together. k1 times k2 times k3, and so on, all the way up to kn. Let's look at some more examples. There are 4 basic blood types, represented by letters A, B, AB, and O. There is also an RH factor, represented by either a plus or a minus. If a local blood bank labels donations according to type, RH factor, and sex of the donor, how many different ways can a blood sample be labeled? So there are 4 possibilities for blood type, right? And every blood type can have either a plus or a minus Rh factor, and one of two sexes, right? So there are 4 possibilities for blood type, 2 for Rh factor, and 2 for sex of the donor. Using the fundamental counting principle, we get this. 4 for the blood types times 2 Rh factors times 2 sexes. That works out to be 16. 16 different ways the blood that the blood could be labeled. Okay. The blood can be labeled. Okay. When determining the number of different ways a sequence of procedures can occur, we will need to know whether or not repetitions are permitted. The next example shows the difference between the two situations. Okay, let's say the letters A, B, C, D, and E are to be used in a 4-letter ID card. How many different cards are possible if letters are allowed to be repeated? Okay. And then for B, how many cards are possible if each letter can only be used once? All right. So, using the fundamental principle of counting for part A, there are a total of, A, B, 1, 2, 3, 4, 5 letters, right? For the first letter choice, there are 5 possibilities. And since repetition is allowed, there are 5 possibilities for the second one, 5 possibilities for the fourth letter, and then 5 possibilities for the fourth one. So I just multiply these together, 5 times 5 times 5 times 5, and this works out to be 625. Right, 625 4-letter IDs, assuming that you can use the same letter more than once in the ID. How many cards are possible if each letter can only be used once? Well, there are still 5-letter choices. So for the first letter, it can be any one of those 5 letters. But after one has been selected, there's only 4 ways we can choose the other one, right? Because we're not allowed to repeat them. And then after the second letter has been selected, there's only 3 ways to choose the third letter, right? Because we can't repeat. We can't use the 2 letters that were already selected for the first 2. And then finally, there's only 2 ways that the last letter can be chosen, right? So this would be 5 times 4 times 3 times 2, or 120. So if repetition is not allowed, the number of potential cards is actually 120. Okay. Let's introduce some notation that will be helpful for the next topic we want to cover here. That is factorial notation. The next couple of counting techniques, we will use factorial notation. The symbol for a factorial is the exclamation mark. In general, n factorial, n exclamation mark, n represents a number. This means to multiply the whole numbers from n down to 1. For example, 1 factorial is just equal to the number 1. But 2 factorial, this is defined as 2 times 1, which equals 2. 3 factorial is equal to 3 times 2 times 1, which equals 6. 4 factorial is equal to 4 times 3 times 2 times 1, which equals 24. 5 factorial is equal to 5 times 4 times 3 times 2 times 1, which equals 120. This is the formal definition of factorial notation. For any natural number, n factorial is equal to n times n minus 1 times n minus 2 times n minus 3 dot 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 until we get to 3 times 2 times 1. Until we get all the way down to 1, basically. N with the exclamation mark in front of it is read as n factorial. 0 factorial is defined as 1. This might seem strange, but it will be explained a little bit later. Okay, let's practice using this notation. Starting here with A, this is 8 factorial. 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. You need to pull out your calculator to do the actual math. This works out to be 40,320. Factorials can get pretty big pretty quickly because you're multiplying a bunch of numbers together. For B, we got 12 factorial over or divided by 10 factorial. There's a little trick we can use for evaluating expressions like this. We don't actually need to multiply out all of the factorials on the top and the bottom. Instead, we can take the factorial in the numerator and just work it out part of the way. 12 factorial is equal to 12 times 11 times 10 factorial. Okay? And if we do it that way and recognize that 10 factorial over 10 factorial is equal to 1, then I can basically take this expression here, 12 factorial over 10 factorial is equal to 12 times 11 times 10 factorial over 10 factorial. The 10 factorials essentially cancel out. And we're left with just 12 times 11, which equals 132. So by doing that little trick, it saves a lot of math, right? We don't have to multiply the 2 factorials all the way out. C. We know that 12 over 10 equals 6/5. Is 12 factorial over 10 factorial equal to 6 factorial over 5 factorial, right? Well, we already figured out 12 factorial over 10 factorial is equal to 132. We figured that out in part B. So let's figure out what 6 factorial over 5 factorial is. 6 factorial over 5 factorial, this is equal to 6 times 5 factorial over 5 factorial. Those 5 factorials cancel, and that result is 6. So no, the two expressions are not equal. They are not equal. Okay, let's talk about permutations. This is the second rule that we can use to find the total number of outcomes for a sequence of events. This is called the permutation rule. An arrangement of n distinct objects in a specific order is called a permutation of the objects. Suppose that a photographer wants to arrange 3 people, we'll say Carmen, Juan, and Christina, in a specific order for a portrait. So we want to list the possible orders, then use the fundamental counting principle to find the number of possible orders and make sure that it matches the answer to part A, and then see how many orders do you think there would be for 8 people. Let's take these one at a time, okay? A. If I were to list the possible orders, we could get something like Carmen, Juan, Christina. Oh, we could get Juan, Carmen, Christina. We could get Christina, Juan, Carmen. What else could we get? We could get Carmen, Christina, Juan. We could get Juan, Christina, Carmen. We get Christina, Carmen, Juan, and I think that's it. Those are the only possible ways that you could specifically arrange these three names in a unique order. There are 6 possibilities. Okay, B, the fundamental counting principle. So when first of all, we want to we're starting with 3 names, right? So when we're selecting a name at the very beginning, there are 3 names to choose from. But once somebody has been chosen to be in the first position, there are only 2 left to choose from, right? So there would be 2 selections to choose from for the next person. And then after the first 2 people have been chosen, there's only 1 left for the last position, right? So that'll be 3 times 2 times 1, which is actually 3 factorial. And that works out to be 6, which is exactly what we found out here, right? Here's the 6 possible ways. The fundamental counting principle also tells me there are 6 ways, right? So this matches the number we got by listing them out. C. How many orders do you think there would be for 8 people? Well, for 3 people, the result was 3 factorial. For 8 people, that result is 8 factorial, which we actually figured that out up here, right? This number, 40,320. That's a lot. 40,320. There's no way we could list them all out like we did here. There's just way too many. So this tells me the number of permutations of n distinct objects using all of the objects is n factorial. This is basically the total number of ways that you could take a group of objects and order them. The total number of unique ways we could order them is n factorial. Okay. Let's look at another example. There are 7 horses in a race and a large jackpot for anyone who can pick the finishing order of all 7 exactly right. How difficult is that? Find the number of possible orders they can finish in. This is a permutation problem because we are interested in the number of ways to order 7 objects. Right? In this case, 7 horses. And using the permutations of n objects rule up there, that result would be just 7 factorial, which is equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. That works out to be 5,040 different ways. 5,040 possible finishing orders. It's basically saying that's the total number of possible ways that you could arrange the horses in order from first place, second place, third place, fourth place, fifth place, sixth place, seventh place, right? Now, so far in calculating permutations, we've used all of the available objects. But what if only some of them are selected, right? Sometimes we might, like in a horse race, maybe there's only prizes that go to first, second, and third place, right? So we might be interested in saying, how many different ways are there to select 3 of the 7 horses and arrange them in order first place, second place, third place, something like that, okay? Let's explore that concept with example 6 here. How many different ways can a pledge class with 20 members choose a president, vice president, and Greek council representative? no pledge can hold two offices. So the order is important, right? So we could answer this using the fundamental rule of counting. If you're selecting somebody to be president at the very beginning, there are 20 choices. But once somebody has been selected to be president, that person cannot also be selected to be vice president, right? So there are only 19 choices that can be selected for vice president. Once somebody has been selected for vice president and president, those two individuals are no longer eligible, right, to be selected for Greek Council representatives. So there's only 18 individuals that can be selected for Greek Council rep. So this result is 20 times 19 times 18. It's just an application of the fundamental rule of counting. This works out to be 6,840. Now, it can also be helpful. In example 6, we used the fundamental rule of counting, but there's also a specific formula that can be used to answer questions like this, called the permutations formula. In example 6, a certain number of objects, people in this case, have been chosen from a larger pool. The order of selection is important and no repetition is allowed because no pledge can be both president and vice president, for example. We call such an arrangement of objects a permutation of n objects taken r at a time. In the pledge problem, n is 20, the total number of people, and r is 3, right? The 3 that we're selecting to fill the 3 roles, president, vice president, and Greek Council representative. We will use this symbol right here to represent this type of permutation. We solved example 6 using the fundamental counting principle, but we could get the same result using the permutations formula, which is this formula right here. Okay. The arrangement of n objects in a specific order using r of those objects without replacement is called a permutation of n objects taken r at a time. It is written using this notation and is calculated using this formula, n factorial divided by n minus r factorial. Okay. Let's do an example where we use this formula. In a lottery game, 40 numbered ping pong balls are put in a bin, and 4 are chosen at random, one at a time. To win the game, players need to match all 4 in the order in which they were drawn. How many different winning orders are there, right? So we're saying, how many different ways is it possible to select 4 ping pong balls from the group of 40 and arrange them in a very specific order? Right? This is a permutation problem because 4 balls are picked from 40 with no repetition, and the order is important. So we will use the permutation formula here. My value of n would be the total number of balls, 40, and my value of r would be the number of balls chosen, which is 4. So we have, when I plug the numbers into my formula, I have 40 factorial on top and 40 minus 4 factorial on the bottom. This is equal to 40 factorial over 36 factorial. Unfortunately, I don't need to work out these two factorials all the way. That would be a lot of multiplication. I can just do this. I can say 40 factorial is equal to 40 times 39 times 38 times 37 times 36 factorial divided by 36 factorial. The 36 factorials on the top and the bottom can just cancel. And so all I need to do is just multiply 40 times 39 times 38 times 37. 40 times 39 times 38 times 37. That works out to be a lot. 2,193,360. This is why playing lotteries is not always the best idea, because of the immense number of possible outcomes that there are. Okay, before we move on to the very last topic, I just want to make one note. In the learning module in Brightspace, there is another short video posted that talks about how to use a standard like scientific calculator to do these calculations. Most scientific calculators have like a built-in function that will do this calculation for you. So you don't actually need to memorize this formula if you know how to use those functions on your calculator. So I would really like for you to watch that video as well, and then practice doing that on your calculator. If you have a scientific calculator, it should have the ability to do these calculations. So I'd encourage you to go do that. Okay, lastly, whoopsies, sorry. I don't actually have, this is actually the last topic for this video. Thought there was one more, but this is the last topic that we're covering in this class. So we're just going to wrap this video up right here. Thank you for watching.